All right, so key terms that you might want to know about robotics is the word end-of-arm tooling. That's a phrase more than anything. I'll tell you now, not every tool on the end of a robot is a gripper. I know that's shocking, right? So this is tooling that is attached to the end of a robot arm to accomplish a given task. We give robots very specific tasks based on what we use them for. Painting, welding, and machine tending are probably the biggest three. A gripper, okay, so let me go ahead and put it this way, guys. A gripper is a category of end-of-arm tool. An end-of-arm tool is not always a gripper. Does that make sense? There is a difference. There is a very big difference between the two. Okay. So teach pendant. This is a programming device used when a robot is manually moved through motions. You have non-volatile memory. This is what is able to maintain its contents when power is removed. So basic operating systems. Most of the programs you create for robots are in volatile memory. Okay. What that means is that I don't care what you programmed it in. It does not remember it after if a power surge goes out. That is why most robots have backup batteries, and you should check those periodically. Why? Because the robots will send you warnings occasionally, but if you forget to heed those warnings, you're not going to be very happy when you lose all your programs. I'll give you for an example. If you've ever been in this other room, you see the little gray line, right? With the little bitty Mitsubishi robot. Yeah, they lost power to it once. They had to get a hold of the people that sold them the line so that they could actually remaster the robot and get it to be back in its program. Think about that for a minute. That's why all the robots carry backup batteries. That's why we try not to turn any of our robots truly off. Because if you do that and remove the batteries, it's like removing the battery out of your computer. It wipes the memory. Not a good idea, right? Just saying. Speed is the maximum rate of motion for a robot arm. You might want to write that down. That's a great test question. Memory capacity is the maximum program size that can be stored in a robot controller. Just like on your computer, right? Y'all know what I'm talking about whenever I say everybody has, I think the basic memory these days is 256 on the cheapest computers, 260 gigabytes. I think the most is we're starting to move into terabytes. So memory capacity is just like with your computer. You get what you pay for. Okay? So a robot is a mechanical device that sometimes resembles a human and is capable of performing a variety of often complex human tasks on command or by being programmed in advance. Sounds very complicated, right? So the term robot is applied to a lot of things. And what we tend to start thinking of a robot as is very different depending upon the circumstances, right? How many of you watch Discovery Channel? Things like BattleBots, right? What makes those a robots over these guys right here? Mm-hmm. Huh? Yeah. Why are BattleBots considered a robot alongside these guys right here? This is why the term for robot is so broad. It applies from everything from industrial robots like these to kid toys. Okay? So it can be a machine that operates automatically or by remote control. A person who works mechanically without original thought, especially one who responds automatically to the commands of others. So these are some different definitions of robots. In the very beginning of all whenever robots first started being created and coming out, they did not think to separate the different types of what they're calling robots. Okay? So robots is very broadly defined for what it is. So the biggest ones we want to talk about for industrial robot is that it's reprogrammable and multi-purpose. Those were the two big buzzwords from last time, right? What that means is that I don't have just one purpose. I can take any of these robots and repurpose them into something else or something to do something else. All right. So then you have industrial robot. This particular definition is a little bit more narrow. A robot is a reprogrammable, multifunction manipulator designed to move material parts, tools, or specialized devices through variable programmable motions for the performance of a variety of tasks. There goes reprogrammable and multifunction again. Those seem to be big buzzwords in these particular definitions. So the field of industrial robotics may be defined as using robot systems for manufacturing. I said I'm trying to paraphrase some of this because a lot of it just gets to be too much. So typical applications are welding, painting, ironing, assembly, pick and place, palletizing, product inspection, and testing. And the best thing about a robot versus human is that they have the ability to do it with a lot of endurance, speed, and precision. Okay? And there are a lot of manufacturers out there. All right, so we did go over last time. Reprogrammable is that you can change a stored program. And then you have multifunction, which is very obvious. It's able to do more than one function. The field of robotics may be more practically defined as the study, design, and use of robot systems for manufacturing. We just said that. All right. So what is manufacturing? We like to throw that word around a lot too, right? Basically, it's taking raw materials, parts, and information and creating a product or service. And manufacturing systems take hardware, programs, and personnel and take that raw material and use it. Okay? You're trying to go from a raw material to a finished material. All right? So the typical industrial robot system, everything revolves around the controller. For those of you that have not figured it out yet, the controller is the giant box that has cables that come out to the robot. It's the robot's brain, essentially. It's where all the computing happens. The arm is just this mechanical device that does what it's told. The controller tells it what to do. Does that make sense? Everything goes back to that controller. So you have your arm, your controller, you have to have some form of power, which what do you think is probably the most common power source used? It's available in just about every country. Electricity, right? The answer to that is electricity. Most common power source is electricity. A lot of robots plug in. That or they run off batteries. And then additional devices, end-of-arm tools, teaching devices, and data storage. So the robot arm is nothing but interconnected linkages and joints and manipulators. The whole purpose of that robot, what is the purpose? Let me back that up. What is the purpose of your arm? Kind of, sort of. What is the primary function of your arm? And in your arm, I'm talking about your shoulder to wrist. What is the whole purpose of this thing? Huh? It's this thing right here. This is your end of arm tool. Our purpose for our arm is to be able to position that tool to move things and to do things, right? Otherwise, what does our arm do all day? It just kind of hangs out close to us, right? The whole purpose of it is to move that hand so that the hand can go in and do the work it needs to do. Make sense? The same thing happens for the robots. The true purpose of a robot arm is strictly to position that tool. That is all it's supposed to do, is position the tool. Okay? We generally are trying to emulate a human arm. So we create specific motions that will enable the tool to reach and do the required work. Okay? Basic drive mechanism is either linear or rotary. Basically, that means that it's either moving in a straight line or it's got a rotational joint. By the way, these guys all have rotational joints. There is nothing linear on them. Okay? They can be moved by hydraulics, pneumatics, or electrical actuators. The robot arm itself is generally electrical. There are times where you use hydraulics and pneumatics. Those are great for flammable environments or environments where you can't have stored energy hazards from electricity because it's an explosive environment or something. But generally, it's electrical. Why? Because electric is very easy to come by, right? Just about every country in the world has some form of electricity somewhere. I will not say they all do, because there are poor countries that don't have electricity. but a lot of them do, at least somewhere. Okay. So the whole purpose of that arm is to move that tool, to get it where it needs to go. So the controller itself monitors and changes the operational conditions of a given robot. It's a very special purpose computer and contains several ports. This allows control of the robot arm, interface with teaching devices and other computers, and performs other communication tasks. Very simple there. Like I said, basically it's the brain. He's sending out signals and he's sending out instructions, and the robot does it. Just like whenever you move your arm, what's doing most of the work? Your brain, right? It's sending out messages to all your nerves and muscles and saying, hey, we're going to take this and we're going to pick up the phone. Hey, we're going to pick up the pen. Your brain does it in a split second. All right, so a lot of the things we connect back to these controllers are things like sensors, other equipment. We try and tie everything together. And we don't always tie it to the controller. Sometimes we'll tie it to an HMI. Anybody know what an HMI stands for? What now? It stands for Human Machine Interface. Everybody knows what I'm talking about, right? You come up, you look at the screen, you tap a few buttons, and things move. All right. So here's a couple of examples. You got the really big cabinet for the big guy over there. This one works for our Moto Man. That's the gray robot right there. Like I said, it works exactly like a computer. So power sources primarily used is electric. There are some hydraulic robots, there are some pneumatic robots. Most of them are electric. Why? Because electricity is plentiful. And you don't have to have specialized equipment. Not to mention, let me put it this way. With hydraulics or pneumatics, if you do not have electricity to run the pumps or the compressor, you're going to have gasoline powered pumps and compressors, which would cost a lot more, right? Much easier to run them off electricity. Not to mention you don't have to change the oil and clean things out as often. So tooling, end of arm tooling or end effector. So there, basically any job you can think of, you can create a tool for. Does that make sense? So welding, spray guns, grinding, deburring, grippers, vacuum cups. The list really goes on and on and on, depending upon the needs of who. Who am I looking at the needs of for this? The needs of the customer. So yes, what am I using this robot for? A gripper is a type of end of arm tool. A end of arm tool is not always a gripper. I will say that several times because everybody tends to think end of arm tool, well, that's a gripper. Not necessarily. It could be a welder, spray gun. It could be a pair of wire clippers. There are other things it could be. So this is a basic gripper. A lot of grippers we tend to think they come down and on and clamp on. But another way you can use a gripper is to what? Is to push out against the product. Is to go down in, let's say if you're trying to pick up a cinder block. Do you want to pick it up from the outside or is it easier to pick it up from the inside? Inside, right? If you can get a good hold on the inside of a cinder block, it's a lot easier to pick it up from there than having to wrap your arms around it, right? So some grippers do the same thing. Instead of trying to get bigger and big enough to wrap around it, they just put it themselves in a hole of the product and expand into it so that it picks it up that way. Okay. But here's some different versions of grippers, and honestly, they come in so many shapes, colors, and creeds. It's literally whatever you need it to do. They've got robots these days that can change out their own gripper. I mean, their own tool. They use electromagnets to hold the tool on, and all the robot does is disengage that electric magnet and pick up the next one that they need. Huh? Really? Those are kind of cool, aren't they? Well, it's better than, let's say, somebody having to walk in and change that tool manually, right? Would y'all agree? Because if you walk in and have to change the tool manually, you run the risk of what? If you forget to stop the cell, you run the risk of getting hurt, right? It increases efficiency because you don't have to have somebody go do that. It also decreases downtime because you don't have to wait for somebody to go do that. Instead, what you have the ability to do is for them to just keep going and going until it decides it can't do it no more. So you got suction cups, you've got this guy that's a actual gripper that's clamped around this piece of, I'm thinking that's beef. Spray painter, you've got this guy who's a drill. This guy's doing some deburring, welding, all sorts of things. So teaching devices are essentially used to make the robot move through the motions. It permits program development and editing while displaying the system operation on the screen. The teach pendant allows direct access to it. So here's the ABB teach pendant. That's this guy right here. He's interesting because you can move only three. What he's set up is he's a 6-axis robot. However, you can only control 3 at a time. You can either control the 2 shoulder joints and the elbow joint, or you can control the 3 wrist movements. Okay. Then you have the Fanic teach pendant. Okay. That's the little yellow robot over here, or the big yellow robot over there. The Kuka teach pendant, which the Kuka teaches in, believe it or not, Microsoft. He runs Microsoft. Kind of cool. And then probably the simplest controller with the fewest buttons besides the Mitsubishi, the Moto Man. Little gray right here. And then the simplest controller of the whole lot is the Mitsubishi. That's the guy on the gray line over there. So data storage devices, non-volatile memory is the very base program. It's what tells the robot to turn on at all. But any program you create, it is always best to do what? Just like if you create a paper on a computer. Save it and back it up, right? Because if the computer crashes, you are out of luck, right? You would be very much out of luck. So you create external permanent storage. I don't know the last time I saw a cassette tape or a floppy or hard disk. I think those have kind of gone the way of the pager and the dinosaur. Very, very rare. Excuse me. CD-ROMs and DVDs are still in use. Flash drives are probably the most popular today. And you have SD memory cards and flash memory cards. These typically are very, very quick to do things. So this is a flash memory card. This is actually what we use with the Moto Man because we have a class called computers. I'm not sure of the full title, but it's computer simulation. What you're able to do is take the robot, program it through your computer, and then put the program on the robot with a flash card. Now, why would that be a useful thing to be able to do? If you drop the information, you're good, but it's something bigger than that. Think Mercedes. If I have to reprogram every robot in Mercedes every year for the next model, that would take forever. What would be their downtime? It would be months, right? Because you'd have to be so finicky and put into certain tolerances and things like that. You would have to be so uber finicky, it's not even funny. So what they do instead, smart thing to do with it, is to not program it directly at the robot. You program it through a computer simulation. And then you add it back to the robot. Then, instead of months of downtime, you're weeks. Does that make sense? Instead of taking 6 months to reprogram that whole assembly line, which probably consists of good 100 to 200 robots at least, you get it done in maybe 3 weeks. And that's only because you have to go in and do touch-ups. Makes life a lot easier. All right, this is something you might want to write down, degrees of freedom. And what that means is that is talking about each joint or axis motion in the arm. It is talking about each joint or axis motion in the arm. Guys, before we so we talked about degrees of freedom. So that's counting the joints and axes in your robot. Which, by the way, the more degrees of freedom or the more joints you have, the more expensive the robot. Make sense? Kind of like the more bells and whistles you have on your car, the more it's going to run you. You have two different types of axes. You have what's called the positional axes. These are the ones that are trying to move the whole arm to get it in position for the job it needs to do. Okay? And again, this is something you might want to take down as some notes. Or highlight it, star it, whatever you want to do. The positional axis moves the whole robot to the proper position. Does that make sense? Okay. So then you have the orientation axes. These are rotating and moving that hand into the proper position. So in other words, let's say I want to pick up this bottle of hand sanitizer. Okay? The very first thing I'll do trying to pick up this hand sanitizer is I've got to move my whole arm to come out and position the arm to grab it. Yeah? Then you have to manipulate your hand until you can get into the position to grab it. Positional orientation. Does that make sense? So again, you might want to have notes about those two because those are great test questions. Okay. So the orientation axes are, how many of you are kind of familiar with military? With the terms roll, pitch, and yaw? In aviation, military, and all that. Well, that is actually how we refer to the wrist movements. Okay? Roll, it's exactly what it sounds like. You're able to roll that wrist around, right? Then you have pitch, which is the up and down rotation, and then you have yaw, which is the left to right rotation. Okay? Does that make sense, guys? So going back to the work envelope, this is everything the robot can reach in its workspace. Okay? I tend to use workspace and envelope interchangeably. It's because they are fairly interchangeable. But this is the maximum and minimum points and everything in between that the robot can put the tool. Okay? So again, just like if you had to sit still at the table, or I got a good one for you, the dinner table. And you have to plant your behind and you have to ask for things to be passed to you because there's only so much you can reach, correct? Same thing. Your workspace is right here at your plate and maybe a little bit of the table that you can reach, right? Because your mama trained you well and you're not supposed to get up and walk around the table to get everything. You're just supposed to be able to sit there during the meal and say, hey, can you pass me this? Can you pass me that? At the same time, you're expected to pass stuff along yourself. That is your workspace or your work envelope. Robot, same kind of thing. Where can it reach inside and out and all the points in between, right? So tool center point. This comes pre-programmed in most robots at the very center of the mounting plate. So if I was to take the grippers off of these robots or the welder off the big one, it has a flat mounting plate. And the original tool center point is at the center of that flat mounting plate. Okay? So this should be the point of action for the tooling attachment. So you have the ability with most robots, if not all of them, to move that point from the dead center of there to wherever you need it to be on the robot. So if my welding tip is out here, I can move it from here to out here. If I need spray to use a spray gun, my spray gun ends here, but my center spray is out here. I can move it there. So it's how you have the ability to move that tool center point from its original position to best have everything work efficiently. Okay? The whole point is to be able to put that tool center point where you need it to be to get the job done. Okay? So in this case, they're showing you a paint sprayer, and where the paint sprays converge is at that point away from the tool itself. And that's the point that you want to be able to control the best so that you can easily manipulate where that paint goes. Yes. Yes. Does that make sense, guys? All right, so robot classifications. So robots are classified according to their workspace. So basically they're classified according to what area can they work in. You have Cartesian or rectilinear. You have cylindrical, spherical or polar. And the final one is articulated, revolute, jointed, or anthropomorphic. Lots of names for the last one. So rectilinear or rectangular, also known as Cartesian. What is Cartesian? You've probably seen it up here a few times where it has the X, Y, Z. It is called the right-hand rule. We actually have turned it into the right-hand rule for robotics, but initially it was for a way of figuring out pitch, roll, and yaw. So everybody take your hand out and do this. You have X, Y, and Z clearly marked now. Z is always up and down. There's a couple of robots that mess up X have X one way and Y the other. But this kind of gives you an idea of where everything's going to move, and you can put it wherever you need to. Its ability to move in almost a square shape. All right. So this is called a Cartesian robot. It moves in X, Y, and Z. You have X moving left to right. I'm sorry. X moves. This is why X and Y tend to get you confused sometimes. X and Y are going to move you left and right and up and down, or and forward and backwards. Z always moves you up and down. So this guy moves in nothing but, let's see if I can. So this guy literally moves inside a box. Okay? This would be his ideal workspace. No, X and Y are left to right, forward and back. Z is always up and down, huh? No. There's some robots that determine that X is forward and backward. Some of them determine that it's left to right. It depends on the robot. I'd like to say that it was easy to determine, but generally you determine it by moving the robot. Some have a little bit of different programming. So the next one is cylindrical. That's this guy right here. He moves in a cylinder. I know it's a terrible picture, but that is a really bad picture. Yeah, I know, I can't draw. Let's see if I can draw a cylinder here. Circle, nope, can't do it. So this one's cylindrical, so it literally sits as a cylinder. It has the ability to turn either way, left or right. It has the ability to move that arm up and down and in and out. It does not have the ability to go over itself or under itself. It is strictly the ability to move in a cylindrical fashion. Okay. The next one is spherical or polar. So it has the ability to turn left or right. It has the ability to move itself up and down and in and out. It has one linear axis here. And then this one's the anthropomorphic. So again, this one would be a what? You can see that it's a Cartesian because it moves strictly in a rectangular fashion. That's terrible. It moves strictly in that rectangular fashion. It has no ability to rotate anything. This one would be your cylindrical. So it's able to rotate around the base, but otherwise all it can do is move up and down and extend and retract the arm. Does that make sense? This one should look a little familiar. This is a drawing based upon the Unimate, which was the what? That was the first robot, the first industrial robot. Okay, so that picture is very close to what the Unimate looked like. So he could only move up and down, move that arm up and down. He was able to rotate his base, and then he had the ability to move that tool as well. So some other classifications. You have a fixed sequence, a variable sequence. Some robots can do playback. Some are numerically controlled. And the word intelligent is misleading. We can make the robot seem like it has intelligence, but does it really? No, it's just a machine. Just like any other machine, does it actually have intelligence? No, not really. So some other terms you might want to pay attention to. I would actually recommend that y'all print this out and highlight these 4 terms, or find a way to take notes on them, because I guarantee you will see it as test material. Accuracy. So this is where the robot can move the tool center point in the workspace when the commands are entered into the controller from the remote terminal. So in other words, how well can it go back to that same point over and over again? Okay? Goes back to that, take a pin and move your arm up and down. What is your accuracy? Not very big, right? Repeatability. How accurately can the controller drive the arm back to a point when the program requires? Okay. Payload. Payload is one of the biggest things. Why? Well, because it depends on if the robot is carrying something or if it is strictly just trying to move that tool center point. So does a welder need to pick up anything but the welder? No. So I don't have to worry about the payload as much as long as I know what that welder is going to weigh, right? However, if I'm picking up, let's say, pool heaters, or I'm picking up pallets of material to ship, then do I have to worry about payload? Yes. Because the thing about payload, that's the maximum weight at which it can carry. So payload is kind of like you. How much can you pick up at the gym? What is your payload maximum that you can grab and move at the gym? What do you think? Depends on what you're doing. Are you doing deadlifts? Are you doing bench press? What are you doing, right? But at the same time, there's still a maximum weight that you are able to move. Okay? So the payload is the maximum weight that is placed from the tool plate of the arm and permits the robot operation within the specifications of accuracy and or repeatability. Now I will tell you, payload does not take into account your tool. Okay, so if I have a robot that is able to move 1,000 pounds, I put a tool on there that weighs 500 pounds. What then can I pick up with that robot? Another 500 pounds. That's why a lot of tools are made of light material and that they try and keep the weight down on them because while still keeping the strength. Because if you overload that, it's just like if you overload your muscles, what's going to happen? You're going to hurt yourself pretty bad, right? A robot is a very expensive thing that you would have to turn around and be able to fix. One of the worst things you could probably do is burn out a motor or burn out anything like that. So payload is something to definitely consider when you're looking at robots. Speed. This is the maximum rate at which the controller can move that center point to a specified place in the work envelope with the payload without over travel or oscillation. So what does that mean to y'all? Well, that means that I'm able to pick this up and move it over, but I don't end up, with my payload swinging. Things like that, because that would be dangerous, yeah? The things you have to consider. So when you're looking at a robot, the very first thing you need to determine is what kind of payload do I have to deal with? Okay? Do I need reinforcement of the robot? Do I need to have bigger motors? What is the payload I'm going to be dealing with? Just like any other tool you deal with, right? Am I going to use an itsy bitsy little screw gun to drywall a house? Or am I going to use a big toy because I want to make sure that this gets done as quickly as possible and at the same time as safely as possible? Degrees of freedom. Like I said, the more joints you add to a robot, the more it's going to cost, right? Just simply because motors cost money, right? Drive power. Again, it goes back to that. Most of it's electric, but there are some ways you can get it as hydraulic or pneumatic. Does the environment require that it has to be hydraulic or pneumatic, or can a motor be used? Okay. Repeatability and accuracy. Work envelope dimensions. If you're working in a very T90 space, do I need to use a big guy like that or one of these little guys right here? You can probably get by using a little guy, right? Speed, memory capacity, just like your computer, memory capacity is a big thing sometimes. Programming support, end-of-arm tooling, and environmental requirements. Okay? Any questions on that, guys? So we've kind of talked a little bit about payload. Again, it is not, the end-of-arm tool is not considered as part of that specification. Why? Because almost none of the robot companies, and I say almost none because there's a few that do, almost none of the robot companies make tools. You can either have those made in-house where you work, or you go to an automation company and say, hey, I need this. Most of the time, the robot companies will not be able to make the tool. In fact, if you tell them you need them to make the tool, most of them think you're crazy because they don't do it. Okay? So it is not part of that specification. All right? So degrees of freedom, so the number of axis, you get rarely less than 3. You have some that are greater than 6. Generally, that's if you get 7, that's a base motion. In other words, you have it running on a rail left to right or wherever it has to go so that it can perform jobs elsewhere. Okay. So you have rarely less than 3 or greater than 6. This one happens to be a 7th because it's traveling on that rail. You'll see the rail under it pretty well. Okay. Drive source. We've talked about this before a little bit. You have electric, hydraulic, or pneumatic. The end of arm tool is typically driven by either hydraulic, pneumatic. Electric is used as well. We use hydraulics and pneumatics a lot because if it's hydraulic, it's because you're trying to use something that's got a heavy load to it. Hydraulic is pretty much the biggest powerhouse that you can come up with. Because think about it this way. How many of y'all have done a belly flop? Water's not compressible, is it? It takes at least that split second of oof before you sink in the water. And when you get out, your stomach's pretty much giant red spot, right? You feel like you just got punched. Because water can be hard. We use the principles of that with hydraulics to create machines that have the ability to do a lot for very little. Okay. Pneumatics is used when things need to be kept clean. The great thing about pneumatics is I don't have to worry about things coming and going. I just have to get it from point A to point B, and then I can just vent air out back up to the air. The only time you would have to worry about returning it to tank would be if you have, let's say you're running pure O2 or pure nitrogen. Then you would have to worry about returning it to tank because that would be kind of expensive otherwise. But generally, pneumatic, we just use basic air, the stuff we breathe. Repeatability, we've already kind of talked about, but it goes back to how well does it go back to that exact point over and over and over again. Accuracy is how much of an adjusting movement does it need to make to reach an exact point on command. Work envelope or workspace dimensions. This is generally given to you. In either a table format or a work envelope drawing. So a table format would look something like this, telling you exactly what degree of rotation or how much extension and retraction you can get with the robot. Or it will give you something like this. This would be the space drawing, basically showing you where the robot can reach at any one time. Does that make sense? All right. We just got 4 slides left, guys, so hang in there with me, okay? Speed. How fast does it go? All right. So a lot of the times, a lot of this is given in English or metric. A lot of it's going to be given in metric. Why? Because metric, I think there's like 3 countries left that use English. And then there's England that has its own standard whatever that it does. It's kind of got a hybrid system. I don't know why. But metric is a lot of what you'll find in a lot of this. They can give you both English and metric since a lot of companies do work with the US. But metric is pretty much here to stay. Like I said, 3 countries that are I think 3 other countries besides us, or we just might be down to 3 in general as to how many are using the English system anymore. And the countries that use it besides us are very small countries. They're not very big. It's very interesting how that has happened over time. But anyway, speed. So how fast can it go? Literally. Can be given as variable speed control or maximum speed if variable speed control is not available. Memory capacity, just like on your computer, right? How much memory does it have at any one point? You can always extend memory by either using flash drives, hard drives, things like that. Um, some robots cut the length of the program just because it can only remember so much or store so much. Um, you have a maximum number of points it can program, or the maximum length of time it will record a program. And we'll get more into that another day. Programming support, what is the quality of the software and programs for the machine? End of arm tool. Most robot manufacturers are not in the tooling business, so it's fabricated either by the end user or somebody the end user contacts, like automation companies or tool and die shops, things like that. Environmental requirements. So if you use a paint robot, do you want the robot to just be standing there, or do you kind of put something over it to make sure it doesn't get paint in all the motors and the air doesn't get, all the paint doesn't get stuck to the robot? Because funny thing about paint, does it strictly stick to the car or to whatever's being manufactured? No. Um, One of the coolest things that has hit the market here lately is people started going into old car plants like Chevy and Ford. And if you go in the paint areas of these plants, since all the paint used to be done by hand, you had overspray. Overspray led to drip dry, right? The paint would drip. So if you look at the rails under where these painted cars would run, you would have giant puddles of paint about yay big. Um, just goes to show you how much paint got wasted. But these days, people actually buy this old paint, cut it up, and sell it as jewelry. It's actually really cool. They actually have named it, there's two different names for it. It's either Detroit agate or say a cutesy little name called Fordite. So if you have to deal with something like painting, you need to make sure everything's sealed up because you don't want paint in your electronics, right? That would probably be the biggest disastrous bit of that, is having paint get stuck all over your equipment. It's not good for it, and it can clog intake valves. So generally, if you have robots in a paint booth, the cabinet is outside so it can stay cool. It's just like your computer, it can overheat. And if it overheats, it's going to melt the innards, and that would just not be good. All right? Make sense? Have y'all got any questions over anything we've gone over today? No? Then